very much. Good morning, everyone. My name is Elaasar from NASA JPL, and I'm here to present you today a paper where we described the work we're doing on model-based system engineering. It's a reporting on a project called openCAESAR. It's about ontological modeling and analysis. And this approach we have started developing 5 years ago in response to years of trying to adopt MBSE on space missions. The approach is trying to solve some problems that we have seen applying the regular MBSE with SysML on large-scale projects. And we noticed pain points. Most of them can be classified under rigor and agility. So the solution we came up with a few years back is trying to balance these two methods. So this is the authors of the paper. First row from JPL and our collaborators from Concordia and Polytechnique Montreal. So I'm going to first do a bit of motivation of why we're doing this work, a little bit about the system engineering like history at JPL, and then I'll touch base on the openCAESAR platform and how it's addressing these pain points. I talked about the balance between rigor and agility, and then some summary conclusions. So as you may know, JPL is a leading NASA lab, a lot of expertise in system engineering, and developer of a lot of space missions. We may be familiar with the Mars rovers, an upcoming mission to Europa Clipper, and an asteroid mission. These are some of the missions that are still ongoing, and we are helping them do system engineering. So, first of all, I want to say that system engineering is information like heavy domain. It includes a large number of people. This group, for example, is just one project, exchanging between themselves a lot of information, mostly through documents. When I say documents, I mean Microsoft Word documents, Microsoft PowerPoint. These are the kind of documents they exchange between themselves. Of course, as you can imagine, this can lead to a lot of errors. You're not sure where is the authoritative source of such document. You don't know how this document was produced. So you can see that it can quickly become an unmanageable or very expensive to manage problem. So what I just described is generally called document-based system engineering. And believe it or not, until today, maybe like 90% of the JPL projects and the industry projects at large are still doing document-based system engineering. So there is a group of projects who have ventured into formal methods, model-based system engineering. And there are a lot of tools in the market that help practice MBSE, model-based system engineering. However, a lot of them are not very integrated, with silo. So that creates also a set of problems, another set of problems. So my team is trying to, we helped a number of projects, especially the large ones, move from here to here. And now we are trying to help them even move to this one, where a model is the central like authority, where a lot of tools talk to each other, they're interconnected. And the whole process is rigorous and agile. We call this integrated model-centric engineering. This is our term for this paradigm. And now, actually, our effort is now moving the projects from here directly to here. So just to give you an idea how things have been going on, this is how a system architecture is produced in the document base. An Excel sheet with gazillion, sheets, color coded so that they understand what is saying what. And so to keep this thing in sync without mistakes, and it's a nightmare. This is the system engineering part. Subsystem engineering is done in a proper way with models. This is the electrical CAD, the mechanical CAD, all these things. But system engineering is done here. So this is where we're trying to get them out of this into models. So with the Europa Clipper project around 2013, it started adopting MVC. It's a big project, like the kind of project that has this many people that we saw. So when they started on this journey, they had to figure out how to do MVC, because out of the box, the tool doesn't tell you how to practice MVC properly. So someone has to figure it out and teach you to the tool. So we tried to do this with system profiles, for example. Long story short, the effort was a step in the right direction. The project benefited from MVC. However, we also noticed up close the issues of applying MVC. And what I have here is a bit of summary what these issues were. Big learning curve, interoperability between tools, the vendor keeps making changes, breaking our tools. It's hard to fragment the model. It's hard to collaborate on models, make changes at the same time. Like all these kinds of issues they were witnessed on the project. So we wanted to make some crack at solving this problem. Still do model-based, but in a better way. So remember, I was talking about 2014 here, where Europa came, but the story started in 2003, where a good subset of our team were original contributors to SysML. And we stayed this much time trying to learn system MVC in general and what it does mean to apply it. We started applying it in 2010, limited adoption. And then we started this program, integrated model-centric engineering, that's trying to push hard on doing it the proper way. And we do it by two things. The Rigor side, we do it with semantic technologies. So semantic web ontologies are still models, but they have logical semantics, semantic technologies. And the other way we do it is the DevOps practices. We try to borrow from software engineering all the practices that make software engineering software development projects more agile, and brought it to model-based system engineering. And the product of this, we call it CAESAR, Computer-Aided Engineering System Architecture. So at this point, we're still using SysML, and we did like a plugin to make the story benefit from ontologies and benefit from DevOps. But then the project kind of graduated out of this, and it started using ontologies with DevOps directly without SysML in the picture in 2016. And then in 2018, we realized what we are building is generic. It's not GPL specific, or most of it was like that. So we took the part that is generic and we open source it, and we call it openCAESAR. openCAESAR is a project from 2018, so it's like 6 years or 5 years now. And the GPL internal CAESAR product is built on top of it. So Rigor means you have to represent information properly and in a way that you can check its correctness, completeness, consistency. Consistency is the most important, because if data is not consistent, you cannot do anything else after. And just happens that with semantic web, this property is easy to check. The agility means you're able to set up things to adapt quickly to changing things around you. A new organization came as a vendor. How can we deal with this? The team grew up, the team shrank, all these. Of course, these are not always easy to apply together. There might be conflicts. For example, writing more documentation is usually a good thing. It improves the rigor, but it's not very agile because things change all the time. So you can see how sometimes this can be at odds. So in order to, when we embarked on this effort, we had to define some high-level criteria that we have to optimize. And we came up with these 7. We want to be rigorous about how we represent information in models with precise syntax and logical semantics so that we can check consistency. We need to make it easy to author models. We need to make it easy to configuration manage, to work in an environment where you can do version control and declare dependencies. Federate, meaning split up the model among collaborating teams, and integrate, meaning collect these models back to do the analysis on them. The analysis has to be rigorously done, repeatable, and the result of analysis has to be shareable with stakeholders. And remember, these stakeholders may not be MBSE folks at all. They could be just people who want to see their data, their information from the model. So you want to present them views that speak to them, that they understand. So when I say the change request process, peer review process, it has to be done for putting in mind such stakeholders. So we had to define an architecture for openCAESAR, and you can see on the left-hand side here, the author side. This is where the information being created. So we defined an ontological-based modeling environment so that we can directly author information in this semantic way, ontologies. However, we still can support existing tools. How? Through adapters. So we can, let's use the current engineering tools through adapters, get them into the ontological format. And then once they're in the ontological format, we can configuration manage, we can do the analysis pipelines, generate the reports, so that at the other end, the system's stakeholders who just want to consume information can look at these reports and judge how the progress is happening on the project. So in the paper, we wanted to describe these things more concretely. So we have a case study. It's a small mission that we try to describe. Of course, this is not one of the real missions, but it's a representative mission. It has the kind of things. We open source it so that research can help us, can understand what we mean, and can help us do more work on it. And you can find it in this repo. So I want to say a little about what does it mean with where to put things into these ontologies. So first, the semantic web has been around for over 20 years. And the main standards there is OWL, the web ontology language, and RDF for how we represent information as triples in a graph database. However, if you try to use these technologies directly, you will find they're a bit not accessible. Sometimes some people will say intimidating. So what we try to do is we try to lower the bar a bit of how to use it. Coming from modeling background and this new knowledge engineering background, we merged them. We created one language called the ontological modeling language. So this language looks like a modeling language. However, it fully maps to ontologies. So when we do analysis, we convert it into OWL so that we can use all the tools from the semantic web domain. But because it's a modeling language, we can use all the tools from the modeling stack as well. So it was very convenient. It allows 2 levels of modeling, vocabulary and description. By vocabulary here, I mean the equivalent of creating a meta model. But instead of just creating it with syntax, this also creates it with semantics. It adds the logical semantics to the vocabulary. And it has a lot of constructs to do this. Some of them are native to description logic directly. and also allow you to write extra rules of inference, such that if you give it to a reasoner, in fact, and there is a lot of reasoners out of the shelf for this kind of logic, it can check the consistency for you. It has features that make it very easy to modularize your models and to make them extensible out of the box. If you're familiar in this domain, there's something called the open word assumption and the closed word assumption. Open word assumption means you can add information as long as you're not introducing contradiction. So we support both. It allows you to build a modeling stack, so a stack of ontologies on top of each other to address the various domains. So you pick an upper ontology, and then you can specialize it for the different domains. And then at the end, you can use it for a project. Kepler is the project. So here, this is the vocabulary stack, and this is the project itself, and you can federate those. It has a textual syntax, graphical notation. We have nice authoring tools for them, textual tools and graphical tools. So depending on what you want to work with, and they're synchronized, you also have the ability to create custom UI declaratively so that you can cater to the needs of your community. Since they are textual artifacts, we configuration manage them in Git, where now you can introduce, have a master branch protected, a feature branch for every change, pull requests, inviting collaborators with you. The whole idea of software engineering, how they collaborate, is now possible to do on models. And federation means you can split the models into different projects and release with semantic versioning from each one, and declare dependency on your downstream with semantic versions. This means here is 7.2. This means I can, if they release 7.3, I can accept it because I say plus means latest. But if they release an 8.0, I will not get it automatically. So by specifying a network like this and controlling these dependencies, you can exactly control the flow of information from the least dependent to the most dependent. 3 minutes. 3 minutes. Okay. What else? We can automate the whole process with CI/CD by generating reports, and we use Jupyter Notebook a lot. And you can find examples of that, where you can generate nice reports for your stakeholders. You can publish it on websites, make them able to report. I want to say that we used these techniques to fix the problem for this project that used the Excel sheet. Now they have a modeling workbench ontologically based. There's a continuous integration process that produces reports that are web-based that can easily review. All right. So in summary, I presented a little bit of the openCAESAR project, its history, what it can do in terms of rigor, semantic technology, and in terms of DevOps, the use of GitHub, CI/CD, all these features. You can learn more about it by visiting the openCAESAR blog. We released all kinds of tutorials, like there's 6 of them now, 1 hour each, where you can get in-depth knowledge about how to use the project. Future work, we are taking this work further year after year. This is some of the topics that we are prioritizing for the upcoming year. Thanks so much.